My name is Katumba Joshua, and I'll be taking you through a machine learning architecture for non-invasive dyslexia screening via behavior telemetry under severe class imbalance. This is group 56. Now, to start with, dyslexia is a common neurobiological lifelong learning disability that affects processing of information. And education experts estimate that about 13% to 14% have such a problem in the school populations. How does this condition affect students? Number one, it makes it difficult for them to read or write properly. And it can affect the way they operate in the academic environments. Now, to address this challenge, we decided to come up with a machine learning model that has an architecture which uses a behavior telemetry and is able to perform dyslexia screening at an early age. We followed a framework known as the DAEL framework. This is the Dyslexia Adaptive E-Learning framework, which was tailored to educational material specific needs of students with dyslexia. This framework was developed in Middlesex University, and it was there to improve the learning experience by adapting to individual dyslexia types. Now, our domain was students who had dyslexia. Those are students that have trouble with reading, spelling, and also processing written information. And the main problem was the students remain undiagnosed due to lack of access to screening tools at early stages. And therefore, there was a need for non-invasive systems that could detect this at an early age. And our goal was to develop a machine learning system for dyslexia screening. But as we're developing that model, we came about certain considerations that we looked at. The first one was how long it takes them to read a sentence or a word. And the second one is how many errors do they make? And the third one was how well they spell or understand the content. So what our model aims to do is to detect patterns in their performance and decide whether the students should slow down, keep up their same pace, or they should speed up. And here are some of the research questions that we developed. The first one was, how can machine learning be used for non-invasive dyslexia screening using behavior telemetry? Number two, which behavior features are more predictive of dyslexia? After that, we came up with objectives. And the first one was to analyze behavior telemetry data. The second was to evaluate model performance using appropriate metrics. Then to look at class imbalance to improve prediction accuracy and to improve learning outcomes and engagement for dyslexia students. Now for methodologies and system architecture, we began with problem identification, then acquiring of data. And as you can see, we use data from Kaggle and datasets, then explanatory data analysis, which involve visualizations and getting a more understanding of the data we're dealing with. Then data preparation, model selection and building, model training, model evaluation, prediction output, and deployment by integrating it via the system. Our dataset had about 3,644 rows, 197 columns, 2 classes, no or yes, then 6 trials, that is to look at clicks, hits, misses, score, accuracy, and miss rate. Then you also had a class imbalance, which had 3,252 non-dyslexic students versus 3,392 dyslexic students. So it gave us a ratio of 9:1. And in order to handle this class imbalance, we used SMART. Now, before SMART, it was 2,601 versus 314. But after SMART, it was 2,601 and 2,601. Our data source was Kaggle. Now, we carried out explanatory data analysis and we came up with figures, tables, graphs, and axes to show more insights about our data. And to begin with, at these bar graphs, we have distribution of gender, which was showing that the males had more dyslexia, had more participation in this study than the females. Then we had people who were speaking the native language, and most of them didn't. Then you had people who were speaking the other language, and most of them did. Then we looked at distribution of age via histogram, and as you can see, it ranges from about 6 years to 16, as I communicated earlier. And most of them having this issue were between 8 years to around 11 years, with 9 years being the highest bar. Then we had dyslexia count, and as you can see, this was the bar graph. Then you had box plots, which were showing the age distribution by dyslexia status. Afterwards, we also looked at gender distribution. We looked at native language distribution by dyslexia status, and also the other language distribution. Then we proceeded to look at the mean accuracy across blocks, the mean miss rates across blocks, and also the mean hits across blocks by dyslexia status. After that, we looked at a correlation heat map, which was showing the accuracy across the blocks. Then we also looked at more box plots. We talk about the miss rate, the mean accuracy, and the mean hits by dyslexia status. Then we came to our models. So we used quite a number of models, but to begin with, I'll start with the extreme learning machine, which had an input layer taking on 196 features. That was for feature engineering. Then we had a hidden layer, which had 128 neurons. Then we also had another hidden layer, which had 64 neurons. And finally, the output. Then we had the tabnet model, which looked at the input features. That was 996 features. Then it had sparse masks, which were there to carry out predictions and also finding patterns in data. And afterwards, it was summing them all together and coming up with an output. Then you had the graphical neural network, which had over 196 features. And then it also carried out graph construction. So we had our k equals to 5, those were the nearest neighbors being adjacent to each other. And then we had the first layer in the graph, then the second layer, and the output. Afterwards, we had a LGBM model, which was taking an input data. Afterwards, it had a number of decision trees, and decision trees would basically take in the data, process it, look for patterns, fix errors, refine and aggregate to give a prediction. Then it also had the CatBoost model, which was having data loading, exploration, preprocessing, data splitting, and then hyperparameter tuning to fine-tune the model, and finally to give us final model. He also looked at the convolutional neural networks, and we had quite many. The first one was the 1D CNN. Then we also looked at the 1D ResNet, and we looked at also a hybrid model of the CNN plus by LSTM and the transformer model. So our model evaluation, we had Tabnet, MLP, GNN, EML, CatBoost, LightGBM, Transformer, CNN, and ResNet, and then CNN plus by LSTM. And in them, our highest performing model was the Extreme Learning Machine. And it's the one we chose in the end. Why? Because it was giving us a more balanced accuracy and also a recall when it came to sensing sensitive data. So remember, in the beginning, looked at the class imbalance, which was a ratio of 9 to 1, meaning that we had to get a model which was accurate. It could predict that someone need to have dyslexia, but at the same time look out for that small class that was finding but was having dyslexia. And as you can see here, in our recall, we had the hybrid model having the highest recall, meaning it was more sensitive, but at the same time, it had a lower accuracy. Yet, if you were to compare it with other models, like the Extreme Learning Machine, it has an 89.4% accuracy, but at the same time, it has a much better recall than the other models to come after it. So it lies within and balances very well as our best model. For deployment, we looked at deploying our Extreme Learning Machine model on huggingfaces.com. So there is a user web browser where someone can input in their data. Then that data is sent via data request to the Python app. Then the Python app sends a model interference call to the job lib, that is the actual model. Then this model carries out prediction. It sends back the prediction results, and later on the response is received in JSON format. Now for model compression techniques, we use knowledge distillation, where we transferred knowledge from the large model to a compressed one. This approach was done, and we looked at 15 ELMs, each with 1,000 neurons, totaling up to 15K neurons. And the lit model was a single ELM with 15 neurons. Then the lit model was trained on some probability scores from the full ensemble. Below are the results that we achieved. And then we looked at model quantization. With quantization, we're lowering the precision of model weights from high precision floats to low precision formats, and applied two main types. The first one was float 32 and int 8. So for float 32 quantization, we organized model storage, cutting size by 50%. Then for int 8 quantization, we converted a 32-bit float weights to 8-bit integers, reducing size by 87.5%. Then we also carried out model pruning. With model pruning, we're removing the least important neurons from the hidden layer. And in our model, we had over 1,000 neurons, so we ended up removing 200 to remain with 800 neurons overall. Then we evaluated the model in the same test after pruning, and we came up with the following results. We had baseline ELM having 1,000 neurons, giving us 83.4% accuracy, and then pruned ELM giving us 83.29, 2.6% accuracy. So in the end, we chose int 8 quantization for production deployment because it provides the best balance of compression, speed, and accuracy. In conclusion, we carried out EDA on 25 visualizations. We concluded with exploratory data analysis on 25 visualizations using our data sets. Then we also deployed our best model. And finally, our study demonstrates the potential of machine learning in enabling non-invasive dyslexia screening using behavioral telemetry data. Our limitations were we did data analysis on past records. That's the first thing. Then we also took clicks and performance, negating things like eye tracking and classroom behavior. And also our model had a very big bias because it had a very big class imbalance of 9:1. In our next steps, we shall look at improving the model performance, conducting a pilot study, integrating the system in real-time screening tools, and looking out for better feature development. So this has been Joshua. Thank you for listening.